Welcome to Unit 2, Lesson 4, the discriminant. So part of this should be review from grade 10. Hopefully you spent a little bit of time in grade 10 talking about the discriminant, and it would have been a lesson that you would have learned right after you learned about the quadratic formula. Because the discriminant is really just one specific piece of the quadratic formula, but it's a specific piece that tells us a lot about how many solutions are actually going to be involved after that formula is calculated. So remember, first of all, that if we have something that's a quadratic in standard form, like we could write in this way, then it can be solved using this very fancy quadratic formula. Negative b plus or minus the square root of b squared minus 4ac, and then all over 2a. But if that's the quadratic formula overall, eventually we realize that there's a specific part of that that is telling us important information. Specifically, this inner part underneath the square root sign, b squared minus 4ac. So we have to think about why that's important. Well, you probably noticed last year when you were first using the quadratic formula why that's important. Because we eventually need to take a square root of whatever is under that sign. And then once we square root it, whatever value we get needs to be both added and subtracted. So sometimes the thing that you would get underneath that square root, b squared minus 4ac, would just be positive or greater than 0. And in that case, you could take the square root and find some value. That value would then be added and subtracted to b, and you'd end up with two different possible answers. That was the most common thing that you probably would have done when using quadratic formula. But sometimes weird stuff happens too. Sometimes when you calculate that b squared minus 4ac, sometimes it might equal exactly 0. That can happen. So sometimes if b squared minus 4ac is exactly 0, then we can easily square root it because the square root of 0 is 0. But then something strange happens when we do the plus or minus part. Because we're adding 0 and subtracting 0, but either way, we're going to get the same result. So we start out looking for two different possible solutions, and if that b squared minus 4ac part is exactly 0, we actually end up with just one single solution. In the strangest case, sometimes b squared minus 4ac might give you a negative value, or it might be less than 0. In that case, we can't actually square root it in the normal way. And when I say the normal way, I mean it won't actually produce a real numbered answer. But now, we can actually take our thinking a step further than you would have last year. Because even though it doesn't produce any real numbered roots, we do know if that is a negative value underneath the square root that it will produce imaginary or overall complex roots. So hopefully now I've convinced you that that special thing, b squared minus 4ac, has a lot to do with how many solutions and what type of solutions we're actually going to be finding in this quadratic equation that we're dealing with. So because b squared minus 4ac is so important, and because you're already getting sick of me saying b squared minus 4ac over and over again, we give it its own special name. That's what the discriminant is. It's that little piece of the quadratic formula that's literally just equal to b squared minus 4ac. Just recapping what it can tell us then, based on all the same things I was saying before. The most common situation you dealt with last year was that that discriminant piece was greater than 0, or in other words, a positive number. So you can then square root it, and then add it and subtract it with negative b if you were doing quadratic formula, and you would find two separate, or we sometimes say two distinct, real numbered roots, or real numbered solutions. And eventually, when you also connected this to graphing and quadratic relations, we also realized that when it's a relation set equal to y, those roots are also our x-intercepts. And so we actually see two distinct and separate x-intercepts in that case if we were to graph out our equation as a relation. The next situation I talked about, though, was, and this sometimes would have happened, when that thing underneath the square root, or the b squared minus 4ac, was exactly equal to 0. So in that case, when you did quadratic formula, you would try and do the plus or minus part, but you'd be adding 0 and subtracting 0, and what you'd realize is you'd actually get two of the exact same numbers. And so last year, you might have thought of that as really just being one single solution, but we're going to think of it now as being two equal roots. So you can still think of it as being two roots have popped up. It's just that both of the roots that you found happen to be the same thing or identical. And what that leads to in the relation form is just one single x-intercept. And we might wonder what that actually looks like. And so that's why we have the little picture here. If we have one single x-intercept for a quadratic, it can only be that way if its vertex happens to be exactly on the x-axis. So that situation is the one that produces that. The final one, which was the weirdest one you probably dealt the least with last year, was this situation. If your discriminant piece, the thing inside the square root, happens to be less than 0. Because then if you're doing quadratic formula, you try and square root it, and that's where you would have just stopped last year. And you would have said, there are no roots to be found here. But really what we say now is that there are no real numbered roots, but it does have potentially two non-real or imaginary roots. What that means though is that those roots don't have any real measured value on the real number line, which means they won't exist anywhere on a regular number line, and an axis on a graph is really just an x number line and a y number line. So a graph is really just like a coordinate system based on a horizontal number line and a vertical number line. But we can't find those intercepts anywhere along our x-axis, along our x number line. We won't actually see them anywhere. And so what that means is that there are actually no x-intercepts in that case. So those are all important things to keep in mind. And again, what this is telling us is that if we simply want to know how many real numbered roots there are, or potentially how many imaginary roots there are, we don't need to do the entire quadratic formula. We just need to work with the discriminant. One last little thing to keep in mind, which we won't play around with too much in this lesson, but it is useful in other cases, so we'll just quickly review it here. If the discriminant value happens to equal a positive perfect square, then the quadratic can actually be solved by factoring. So if you're ever trying to solve a quadratic equation and you don't want to necessarily have to go through the entire thing of factoring it just yet, or you don't want to necessarily have to do the entire quadratic formula because you don't know which is going to be the best method, if you take a minute and figure out what the discriminant is, whether or not it's a positive perfect square will tell you whether or not it can be factored. Let's put that thought on hold for a moment though, and just go back to the general things we were saying about the discriminant. And let's now try and use the discriminant to figure out the nature of the roots. And when we say the nature of the roots, we mean, are they distinct or different and real? Are they real but two of the same points, or sort of like one single overlapping point? Or are they two imaginary roots? That's what we're trying to find. So this is the one that we're starting with, and we could just use the a, b, and c values that we see and start calculating out its discriminant. But when this is in an equation form, we can also do some tricks to it to try and make the numbers simpler to work with. So for example, everything on the left side nicely divides by 4. So I can actually divide both sides of my equation by 4 because I can also take my right side and easily divide 0 by 4, and I won't even change the right side at all. So what I'm actually going to do, and I'll just show you this here, is I'm taking this whole thing and I'm going to simplify the numbers I'm working with by dividing it by 4. So this is just a trick that you can use as well to make the numbers from there easier to work with. And it's still equal to 0 on the other side. So from here, that means my a value is not 16. I can deal with a smaller a value now of simply just 4, and my b value will be -4, and my c value is 1. So I work out my discriminant, which is b squared minus 4ac, and it's equal to -4 squared minus 4 times another 4 and times 1. So Negative 4 squared is 16. And then I'm subtracting, well, 4 times 4 times 1 is also 16. So when I break that down and actually come up with a final result for my discriminant, I get exactly 0. So what is that telling me? Well, now I make a little two-part statement here. I start with a since statement. So remember, since is like an upside down therefore symbol, upside down triangle. Since my discriminant was exactly equal to 0, I can say therefore, well, that's true when we have them exactly equal to 0, there are two equal real roots. So equal is the key. If this had been greater than 0, we would also have two real roots, but they would be two what we call distinct real roots. And distinct is the word we're going to use for different than one another. But here we have two equal real roots. And we don't actually have to find what they are. We're just curious right now how many roots and what type there are. So we found that. Let's try the next one now. Here, we're not going to divide anything to try and make it simpler, but we should make sure that we get this into its proper standard form, which means we just need to rearrange the terms that we have on the left side a little bit. So it looks more like this. And then that allows us to more easily identify the values that are going to go into our discriminant. So in this case, b squared minus 4ac is going to be negative 2 squared minus 4 times negative 3 times positive 1. Or in other words, positive 4. And then I've got minus 4 times negative 3 times positive 1. So that's sort of like I'm doing subtract negative 12, or in other words, it's like I'm adding 12. So I really just get positive 16. The number 16 itself isn't really that important. What's important about it to note is that it's greater than 0. It's a positive number. That's what I need to make note of. So now I make my two-part statement and I say, since my discriminant is greater than 0, I can say, therefore, once again, there are two real roots, but now I'm going to say two distinct real roots. And that word distinct, again, just means different, and it's a very important word here, distinct real roots. So they are distinct, they're two different ones, and it's important to note, they are real as well. They are real numbers. And let's try one more. Now this one looks really funny looking, but let's rearrange it into something like a standard form and then work with it from there. Well, if it's going to be in standard form, we should put everything all together on the left side and 0 on the other. So the negative x squared, I'm going to move to the other side and become positive x squared. The positive 2 root 2 times x moves to the other side and becomes a negative term. And then I still have a positive 3 that was already on the left side. So you might be tempted to try and do more things with this to make it simpler in some way, but we don't have to. We can actually just use the coefficients we have. So this would be like a coefficient of 1 on our x squared. And now we'll just use this entire thing, negative 2 root 2. We'll just use that as our entire b value. And then our c value will just be positive 3. And that's okay. I know our b value looks a bit strange, but it's still just going to be a number that we can work with in calculations. So a is 1. We're going to use a b value of, again, it's negative, so be careful of that, negative 2 root 2, and a c value of positive 3. So b squared minus 4ac in this case is going to be, well, negative 2 root 2 needs to get squared, and then we need to subtract 4 times 1 times 3. Well, negative 2 root 2, when we square it, it's going to become positive. And 2 squared is 4. And root 2 squared is 2. And then 4 times 2 is 8. So that thing works out to 8 when it gets squared. And then minus 12. Or in other words, the full result is negative 4. And once again, the actual number part, the 4 itself, is not really important. What's important to note is that it's negative. It's less than 0. So I make my little two-part statement, and I say, since my discriminant in this case was less than 0, therefore, there are still 2 roots, but they are non-real roots. That's what we're going to say. That's the key word, is non-real. I would also accept imaginary if you want to say it that way, but they are non-real roots. I'm going to try and even avoid just using the word complex here, because remember, technically real numbers themselves, real numbers are just one branch of complex numbers that don't have any imaginary part to them. So I can either just say that these are non-real roots, or I can say that they are purely imaginary roots, and either way would be technically correct. In the second portion of this lesson, we'll see how we can use the discriminant to sort of work backwards and see what possible values for an unknown piece of our equation could have produced each of these different scenarios. So this second portion asks us to determine the values of k, or possibly if there's just one value of k, then we'll find that as well, that will give the indicated type of roots. So what do we mean by that? Well, let's take a look at this first situation. Here we're given what looks like a regular old quadratic situation on the left side, except that we seem to be missing a coefficient. So in all of these cases, one of the pieces, or essentially like one of the pieces of your coefficients, will be k, some unknown value. And we're trying to find what values of k, or in other words, what values could we use to complete this equation that would still produce a situation that had distinct real roots. Remember, that means 2 different roots that are real numbers. Well, what would the discriminant be in that case? The discriminant would have to be such that its value was greater than 0. So if we want this all to be true, we need to find a way to make sure that this strange looking quadratic that we started with always has a discriminant value that's greater than 0. So really now we're asking ourselves the question, what possible values for k would make sure that the discriminant stays greater than 0? Well, in order to do that, let's step back for a second and think about what a, b, and c actually are for this situation. So the a value is the thing we don't know. The a value is just the k thing that we're looking for. So the a value is just going to be a k for now. We're going to use a separate variable just to hold its place. The b value is -2, and the c value is +1. Let's substitute those in, as is, into our equation for the discriminant. So it would be -2 squared minus 4 times k times 1. Or in other words, that's like, and I should say, sorry, that's still greater than 0. That whole thing has to be greater than 0. So that would be like 4 minus 4k has to be greater than 0. So we still haven't solved anything yet, but take a look at what we have now. All of a sudden, this scenario is the exact same type of situation we just spent our entire last lesson learning how to deal with. So right now, we have a variable k that's part of not an equation, but an inequality statement. So we need to find what values of k will make sure that everything we have on the left side stays greater than 0. Well, we can use all those same rearranging skills that we learned last lesson. So I'm going to subtract 4 from both sides, which means -4k has to be, in this case, greater than -4. And then I want to get k all by itself. So this is the tricky part that we have to remember from last lesson. I have to divide both sides by -4. But when I divide by a negative, I have to switch the direction of my inequality sign. So k can be all by itself, but now I've divided by a negative, so it's going to be less than, and when I do -4 over -4, it's just +1. So remember, this had to switch because we were dividing by the negative that was attached to our k value in the previous step. So, in other words, we've determined that as long as we always choose a k value that's less than 1, really anything all the way up to 1, but still less than 1, as long as that is our k value, we will always produce an overall quadratic equation here that will have two distinct real roots. That's what we found. And so that k we sometimes call a parameter value, some specific value that completes an equation that could take on different possible values depending on what type of equation we're trying to build. So now we know we can always build an equation with two distinct real roots as long as this k value in this case stays less than 1. Let's try and build some other equations in different values for k. So in this case, now we want to figure this out so that it has equal real roots. Well, if it's going to have equal real roots, that means its discriminant must be exactly equal to 0. So now we have to ask ourselves, what sorts of values for k will make that discriminant exactly equal to 0? Well, again, let's think about what we would sub into the discriminant. Our a value. This is a little bit weird. Our a value is just always whatever's attached to our x squared, though. So how about we just make this entire bracket our a value? So our a value is just 1 minus 3k. And anywhere we sub it in, we'll just make sure we keep a bracket around that whole thing. Our b value is 4, and our c value is -4. So let's substitute in. B squared would just be 4 squared, and then it's -4 times a. So I use a bracket and replace a with 1 minus 3k. And then I also replace that with a -4 for c. And that's still got to be exactly equal to 0 on the other side. Let's start to simplify this a little bit. That would be 16. And then I have a -4 coefficient multiplied by a -4 here. So I'm going to turn that into a +16 coefficient in front of this bracket. And then I'm going to expand that 16 in. So plus 16 and then minus 48k still must be equal to 0. Or in other words, 32 minus 48k must be equal to 0. And now I actually don't even need to rely on skills from our previous lesson because this is not an inequality, this is just an equation. And in fact, it's just a linear equation because the highest exponent we see on k is just a 1. So we just solve it the same way we would any other equation. So negative 48k, if I subtract 32 from both sides, is going to equal -32. Then I divide both sides by -48. So k is equal to, and I end up doing a negative divided by a negative, so it really just equals +32 over 48. But both of those can be divided evenly by 16. So more simply, I would say that k in its simplest form is actually 2/3, 2 over 3. So again, what that means, going back to our original situation here, what that means is that in this overall equation that we started with, if you sub in a k value of exactly 2/3, you will produce a situation that produces equal real roots. Or if we want to think of it on a graphed relation, it would produce a single x-intercept at its vertex point. But again, it only works for that one specific value of k, and that's true when we're looking for equal real roots. Let's try some others that might involve inequalities again, though. So now for this one, we're trying to find a situation that'll produce non-real roots. So non-real roots, what does that mean? Well, it means imaginary roots, and which ones produced imaginary? Well, it was when our discriminant was less than 0. When that discriminant that's underneath the square root in quadratic formula ends up being negative or less than 0. That's what produces those non-real roots. Well, the a value we're going to use is 2. And the b value we're going to use now is going to be the thing that involves k. It's going to be negative k. And our c value will be positive 8. So it's going to be negative k squared minus 4 times 2 times 8. And that whole thing has to stay less than 0. Or in other words, k squared minus 64 has to stay less than 0. Well, that stuff that I have on the left side is not only a quadratic, specifically, it's a factorable quadratic by difference of squares. K minus 8 and k plus 8 must be less than 0. So in other words, the roots of this, or the zeros themselves, are k equals positive 8 or k equals negative 8. And I also just note that the expression that I'm looking for here, this quadratic expression that I have on the left, is supposed to be less than 0. So if you go back to our previous lesson on quadratic inequalities, we know that when we're looking for our quadratic expression to be less than 0, and we found the 0 points, then the values that we want for k are all of the points in between our zeros. So I can even maybe just take a moment and graph out what that looks like. And then again, when I say graph, I just mean on a single number line. So we'll put negative 8 down here somewhere. We'll put positive 8 up here somewhere. And it's never going to be equal to either of those, which means I'll put open circles in both spots. It'll never be equal to them, but it can be any value in between them, as long as it's a little bit less than 8 and slightly more than negative 8. The other way that we state this, here's a different way to think about it, is that, let me just change that, there we go. Another way to think about this is to say, therefore, and here's how I'm going to write it. I'm going to put negative 8 here at the beginning. I'm going to put k in the middle, and I'm going to put positive 8 at the end. So it's sort of like, I sometimes call this the sandwich method. I am sandwiching the k in between its lowest possible value and its highest possible value. So when I write those three things, I can arrange my inequality symbols so that they open towards the right in both cases. So essentially what I'm saying here is first that k always has to be greater than negative 8, but I'm also saying that k always has to be less than 8, which is a way of saying that k overall is going to be sandwiched in between negative 8 and positive 8. So that is the sort of statement that we can make that indicates that overall. Let's try one more that's going to look very messy, but I promise you we can still work with it. So this last one, it doesn't say necessarily distinct real roots. It doesn't say that they need to be the same real roots. It just says we want there to be real roots. So what does that mean? Well, it just means they can't be imaginary, or they can't be non-real. So b squared minus 4ac, or our discriminant, if it was going to be distinct real roots, it would have to be greater than 0. But if it was going to be the same or repeated real roots, then it could be equal to 0. So really we're looking for what would make our discriminant greater than or equal to 0. The only thing we have to avoid is when it's less than 0, because if it was less than 0, we would have non-real roots or imaginary roots. But here's where it gets a little messy, because now I need to think of my a coefficient as this entire little binomial 2k minus 1. Similarly, B is also going to be a binomial that involves K, and C is as well. K minus 1 in that case. But again, substitute it all in the same way that you're used to. It's just going to lead to a more complex polynomial that we'll have to deal with. But if it still ends up being linear or quadratic, then we'll still be able to tackle it with similar strategies that we used in our previous lesson. So now we need to do b squared first. So that's 3k plus 2, and we square that whole bracket. Minus 4 times a, which is 2k minus 1, and then times c, which is another k minus 1. That whole thing has to be greater than or equal to 0. Now I can start to expand out. So 3k plus 2, when I multiply it by another 3k plus 2, it expands out eventually to 9k squared plus 12k plus 4. Then in the other one, I'm going to have minus 4 times, and I'm going to create a big bracket here to represent what the other two binomials would multiply out to. 2k squared minus 3k plus 1. And all of this still has to be greater than or equal to 0. So let's do a final expanding and simplifying couple of steps. So I'll keep these terms as is for now, and expand by negative 4 in. Now let's simplify and collect some like terms. We end up with just a single k squared term. Then we have 12k plus another 12k. We end up with 24k. And then we have a plus 4 and a minus 4. So actually those terms without a variable attached just cancel one another out. They have to be greater than or equal to 0 still. And now we have a quadratic on the left side, and it can be factored pretty easily using common factoring. So I can pull a k out and leave another factor of k plus 24. That all has to be greater than or equal to 0. And so the zeros themselves from this quadratic expression I have on the left are k equals 0 itself and k equals negative 24. And so it can be equal to those exact values themselves. That's totally okay. But it also, if not that, has to be greater than 0. And so again, if you remember from our previous lesson, if you go back and review solving quadratic inequalities in our last lesson, when our quadratic expression needs to be greater than 0, we're looking for our solutions to be outside of the zeros. And let's graph out again what that would actually look like. So here's our little k-axis. I'll put negative 24 way down here, and I'll put 0 maybe here. And remember, it is okay for it to equal those values. So I'll put full solid dots on those points. And now instead of using all the k values in between, it's all of the k values outside of those. So in other words, from negative 24 farther down into the negatives, and from 0 towards the positives from there. And a different way I can state that is using two separate mini inequality statements. In other words, saying that therefore, k could be less than or equal to negative 24, or k could be greater than or equal to 0. So I can't really accomplish that all in one sandwich statement, the same way that I did when I was summarizing my results in answer C. But for this question, I would just have to write it down as two separate statements. So either k is less than or equal to negative 24, or it could be greater than or equal to 0. In general, what you're seeing now is that this lesson is just taking some skills related to the discriminant that you would have learned last year, and now combining it with some of those important skills related to solving both linear and quadratic inequalities.